Maybe this will sound banal, but the universe is vast, and its scale is truly incredible. Right now, we are living and revolving around a star at a speed of 29,765 kilometers per second, covering 940 million kilometers in a year. Our Sun is one of approximately 400 billion stars in our galaxy, which also revolves around a supermassive black hole located at the center of the Milky Way at a speed of about 220 kilometers per second, completing a full rotation around the center of the galaxy in approximately 250 million years. The size of our galaxy, the Milky Way, is approximately 100,000 light-years in diameter, but even it would look like a speck on the background of the entire universe. So why is the universe so vast? And perhaps the most important question of all, how big is the cosmos really? The diameter of the observable universe is estimated to be about 93 billion light-years. It is believed that this space contains up to 2 trillion galaxies. Assuming that all of these galaxies are similar to those we can observe today, there could be up to 1 septillion stars in the known universe. However, they still make up only a small percentage of the actual scale of the universe, which could be hundreds, thousands, or even billions of times larger. The first thing to consider is what we mean when we say, universe? The universe is defined as all of space and time, every point in space throughout its lifetime. Space is the volume in the universe, a three-dimensional field that lies beyond Earth's atmosphere and serves as the vast background of matter in the universe. Time, on the other hand, is the constant flow of causes and effects in this space, the catalyst for life, death, creation, and evolution. Space and time are fundamentally connected and unified, forming a system of almost unfathomable complexity known as spacetime, often referred to as four-dimensional. In this model, space represents 3 dimensions, and time is the 4th dimension, with any cross-section of a 3-dimensional cube along this axis representing the universe at a specific moment in time. Our understanding of spacetime and many other scientific ideas was postulated by Albert Einstein. He understood space and time like no one before him and gave us 2 fundamental foundations that we use to model our present reality. In 1905, Einstein presented his special theory of relativity, thus changing our understanding of light, mass, and energy. Then, in 1915, at a meeting of the Royal Prussian Academy of Sciences, he presented his general theory of relativity, which provides a comprehensive interpretation of gravity, space, time, and their relationships. These elegant theories have existed in science for over 100 years and form the basis of much of our current knowledge about our universe. According to Einstein, mass is a form of condensed energy that distorts the plane of space and time that outlines our universe. The resulting curvature of this plane is felt as gravity. Gravity is the effect of objects attracting each other by distorting spacetime. It is one of the simplest yet deepest fundamental forces in our universe. Nothing special is required here, just mass. If you have mass, then you have gravity. And that's why it dominates the behavior of the universe at all levels, from interactions at the level of small particles to the large-scale behavior of galaxies. We owe the latter discovery to astronomer Edwin Hubble, who made a series of innovative discoveries. Before Hubble, it was believed that the universe was static, in the sense that it was neither expanding nor contracting, and was entirely populated by stars and nebulae in all directions. However, in 1924, Hubble discovered that one of the so-called nebulae was actually a separate cluster of stars, similar to the Milky Way, but much farther away than previously thought, leading to the discovery that the Milky Way galaxy is part of a larger universe of thousands, and possibly even millions, of galaxies. In 1929, Hubble made one of the greatest discoveries. He noticed that the universe was not static, but expanding. This discovery, along with Einstein's theory of relativity and the work of other great scientists, became part of our current cosmological model. This model is the lambda-cold dark matter model, which is well established and documented, although not without shortcomings and unanswered questions. Nevertheless, it remains our best attempt to understand the origin and nature of the universe. Central to all of this is the Big Bang Theory, the idea that the universe originated from a point of extremely high density and pressure. Since we know that our universe is constantly expanding, if we trace this continuous process back to the beginning of the universe, we arrive at a point where the universe was microscopic and compressed before it began to expand. We do not know how or why this happened, but there is evidence that the universe was smaller and hotter about 13.8 billion years ago. However, previous times cannot be tested in the realm of physics. But we believe that in the earliest nanoseconds of the universe's life, something suddenly and radically caused it to expand due to an event known as cosmic inflation. This occurred at a rate faster than any known velocities or laws. The tiny universe at that moment was at least 10 times smaller and was increased to a volume of 78 degrees. Each nanometer of space stretched more than 10 light years. And this happened in less than a fraction of a second. We do not know what the overall space of the universe was like after this inflationary epoch, but it meant that the inner part of the universe suddenly scattered much more thinly, giving it more energy for something to happen. After inflation, as the temperature of the universe continued to drop, the energy within it concentrated into a giant universal plasma and then broke apart into the first particles, and later into subatomic particles such as protons and neutrons. But let's jump forward almost 14 billion years to our current time. The universe is enormous and filled with much larger and richer structures. Atoms gathered into gas clouds, and gas clouds became stars. Today, most of these stars belong to enormous ancient galaxies. Most of these galaxies are clustered into groups and superclusters, which are connected by threads of dark flow consisting of diffused hydrogen, forming a cosmic web. When we talk about space, we mean the observable universe or the universe known to us. It is a spherical geocentric region of space consisting of all the galaxies and matter that can be seen or detected from Earth. The cosmic horizon is the boundary of our observable universe, and the light from distant galaxies located at the edge of this horizon has traveled for almost 14 billion years to reach our telescopes. But because of the regions beyond this cosmic horizon, the light has either not yet reached the solar system, or there is something that absorbs photons and does not allow them to escape. However, while the universe is slowly but surely increasing our field of view, it still depends on the location within the galaxy where we are located. But astronomers say that beyond the cosmic horizon, the speed of light and the age of the universe are no longer compatible. That's why we are limited by our observable universe, segmented and separated from the full scale of the cosmos. Because of this, we cannot make an accurate conclusion about what may lie beyond the boundary. But considering that the universe seems to be relatively isotropic on large scales, we can expect even larger clusters and superclusters of galaxies. But the question arises, how much is out there? As expected, it is difficult to answer this question, and the estimates we have to date depend on the curvature of the universe and assumptions about its shape, which still represent a gray area in cosmology. I will skip some very complex mathematical scientific calculations here, but briefly note that the best estimate made to date by physicists at the University of Oxford is that the total area of the universe should be at least 250 times larger than the radius of the observable region. Thus, the total diameter of the universe is 23 trillion light-years. This means that the observable universe has a diameter of 93 billion light-years, which is only 1/15 of its overall size. If there are 2 trillion galaxies in our observable universe, then there could be up to 30 quintillion in the unobservable universe. To be honest, we may never know the exact size of the entire universe, but given the numbers discussed here, it seems almost inevitable that there must be life somewhere else in space. On a local scale, the expansion of the universe is very weak, so gravity is able to hold objects such as galaxies together regardless of how large the universe becomes. However, Massive cosmic voids between galaxies and clusters of galaxies are growing from within their dark depths, gradually separating galaxies and galactic groups, such as our local group, isolating them in their own galactic pockets. But because of dark energy, the expansion of the universe continues, and according to astrophysicists, space will eventually expand so rapidly that even our closest galaxies will move away from us too fast and disappear beyond the visible horizon. This will continue until the nearest galaxies to us are thrown beyond the cosmic horizon, and even our local universe will become invisible. In the very distant future, the view from every galaxy of the universe will end with its own stars, and beyond its outer edges there will be nothing but empty and cold darkness. We will never be able to see another galaxy again, as distant galaxies can no longer merge and will eventually stop producing new stars. The Milky Way and Andromeda galaxies will merge before this happens, but the newly formed elliptical galaxy will gradually burn all its stars. There will inevitably come a time when all the stars in the universe will either go out or explode, leading to the darkest of times in the universe. But until then, it's still very, very far away. So write comments, like, and most importantly, take care of yourself and your loved ones. Huge thanks to everyone who supported me. All the best to you, dear friends. And until new, even more interesting space encounters.